我们今天下午有3个演讲者，我们3位同学都上线了吗？我看好像都在，对吧？在线了吧？
你好，能听到吗，张老师？
可以，可以，可以，
在线了，在线了。
可以，可以，行。佳明
在线的，
在的，对吧？行，好。
在的，在的。
要讲的要注意时间，因为我们的时间比较短，每个人只有20分钟，但是实际讲是讲17分钟，好吧？然后留3分钟给别人这个回答问题。
好的，好的。
好，
好的，老师。
我可以开始了。
Okay. Okay, it's the time now. I'm the chair of this session. I'm Xiangchao Zhang from Fudan University. And in this session, we will have three talks. The first one will be Mr. Chen Ronghan from Shenyang Institute of Automation, Chinese Academy of Sciences. Okay, now let's welcome.
Okay. Thanks for the introduction of Professor Zhang, and thanks for inviting me. It's an honor to be here to give this talk, and I welcome everyone to listen. And today I'm going to talk about 3D object recognition and pose estimation techniques for robot manipulation. Here is the outline of my talk, and my talk will divide these methods into traditional and deep learning-based methods. And I will introduce 2 recent works from our team in which we propose a traditional handcrafted geometric feature with specific LPS and an unsupervised geometric feature. Okay, so here I will begin with introduction. And as the development of robotics, robots are applied in more and more scenarios to perform various tasks, from beam picking, maintenance of satellites, underwater recovery, to tasks in kitchen, such as making pancakes. And robot manipulation is the key technology for robots to perform these tasks successfully. So imagine you were blindfolded and you need another person to guide you to turn on the tap here. So what information would you expect that person to tell you? So first of all is where the tap is, and it is also just the location. And secondly, you'll need the orientation of the handle here, and the combination of them is pose. So here we'll introduce some mathematical representation for pose. The location is often represented as a 3D vector x, y, z. Thus, it is 3 degrees of freedom, and the orientation is also 3 degrees of freedom and can be represented as theta x, theta y, theta z, which are the rotation angle relative to axis x, y, z here. And besides, there are also other representations for axis and angle. The vector x, y, z here specifies an axis, and the angle theta is the angle that rotates around the axis. And the quaternion is an extension of complex number and can also be seen as a 4D unit vector composed of Qi, Qj, Qk, and Qr. And together, the pose is 6 degrees of freedom and usually represented as xyz and zy, zx, and zz. So here I will introduce some common 3D data representations used for robot manipulation, including multi-view images, voxels, point clouds, and meshes. Multi-view images just some images from different views, and voxels are a set of cubes divided by grids. It has cubic complexity, thus often have low resolution. And point cloud is a set of points. It can be directly obtained from sensors. Thus, they are most widely used in industries. And meshes are composed of faces. It contains topological information and is often used in graphics. And with rendering techniques, 2D images can be generated from it. However, it requires heavy pre-processing to obtain high-quality meshes. So, what's the pose estimation problem? Given an input image here, the pose estimation problem aims at determining the pose of the model in the image under the coordinates of the sensor here. So in this talk, we mainly focus on the instance level pose estimation, which means the 3D model of the query object is given, and they are only under rigid transformations. So we've known the importance of the pose to robot manipulation, but how exactly does pose estimation help with it? So here, as an example, I will introduce the most basic task in manipulation, the grasp task. So here's the pipeline of pose-guided grasp. First, the 3D model of an object is given, and the grasp label can be obtained by manually annotating, simulating, or analytical methods. And then they can be stored and construct a grasp database and store them offline. And then when testing online, we first recognize and localize the target using segmentation or detection techniques. Then the pose can be estimated. So since the object is rigid and the grasp labels in the database can be directly transferred in the scene using the estimate pose. Thus, under these circumstances, when grasping online, no further computation is needed, and the grasp problem is almost equivalent to a post-estimation problem. So here we first introduce traditional methods, and these methods often perform object recognition and pose estimation simultaneously. Typically, the pipeline of traditional method can be divided into 3 stages. First, features are extracted from input data, and different strategies are applied to generate rough hypotheses. And finally, the hypotheses are further verified and refined. For feature extraction, different features can be divided into local and global ones. Global features encode properties of the entire object, which are good when object is textureless or smooth. Local features are designed to encode texture properties, geometric properties, or both in the local region. Geometric features are naturally invariant to light and scale variation and contain rich geometric information, thus they are widely used in real applications. So, and in second stage, extracted features are used to generate hypotheses. Generally, they can be divided into template-based, response-based, or voting-based methods. For template-based strategy, the model are first rendered in 2D images from equally sampled viewpoints, and then global features such as background boundaries or edges are extracted as templates. And then finally, the templates are matched with features extracted from the scene. Hierarchical post tree or lane mode are pre-processed to accelerate the matching process. However, it's sensitive to occlusion and noises, and it's hard to generalize to unseen poses. Correspondence-based strategy extract local features to construct 2D to 3D correspondence or 3D to 3D correspondence. For 2D to 3D, they use PNP algorithm to solve for the pose, and 3D to 3D can obtain the rotation or translation parameters by solving a least-square problem. And vote-based methods also use local features to find matches. For indirect voting methods, several key points or corners are predefined. When constructing the database here, both the features and their offsets here related to the key points are saved. And when online testing, each match can restore the location of the key points based on pre-saved offsets. The key points with highest density of the votes are selected, and the final pose can be solved by correspondence-based method. And direct voting method can directly vote the center. In addition, it can also vote the orientation by constructing a local reference frame, also known as LRF, which we'll cover later. And so the direct vote strategies doesn't need to solve PNP or least square problem. This is more efficient and robust. And in the verification and refinement stage, these hypotheses are filtered by setting thresholds or merged using clustering methods, and the ICP is usually used for refinement. So here I will introduce the local reference frame LRF as shown in these images. They are often constructed for feature extraction, since you can always rotate the LRF in a canonical frame to stay rotational invariant, and it can be constructed by compute a covariance matrix of the local points and then perform eigendecomposition. And eigenvectors are assigned to be x and y-axis based on magnitudes of eigenvalues, and the axis z is their cross product. And we mentioned that LRFs can be used to vote for orientations, but can they always be stably restored? And the answer is no. And so the main problem is symmetric. And for a local symmetric surface like this, though the axis z here can be stably restored, but the direction of axis x or axis y is difficult to determine, which makes the restoration of LRFs very unstable. Thus, only the asymmetric features are reliable, and this can cause wrong predictions for or a decrease of number of features. Thus, this can have a bad influence on the pose estimation. So, we propose a geometric local feature with specific local projection statistics VSLPS to solve this problem. The key idea is that we introduce the line of sight represented as vector 3 here to eliminate the ambiguity. Since the LZ can still be determined stably, we define LX as the cross product of LZ and V3, and LY is the cross product of LZ and LX. And in this way, our VSLPS can stay invariant under the same viewpoint. Here is the pipeline of feature extraction. Based on proposed specific LRF, VSLPS extracts geometric descriptor by calculating statistics of local projections. First, the local neighbor points are transformed into the LF here, then projected into these three planes, and the normal, distance, and color distribution matrices are constructed, and they are further compressed to by computing the central moment or channel attribute, and the final feature is a 135-dimensional vector. And sorry. And here is main pipeline. It consists of offline database construction and online testing. And in the offline stage, the model is first rendered from random views to generate RGBD images. And then the features are extracted to store in the database. And when online testing, we use the robust direct voting strategies. And we test our methods on several datasets. On LCHF dataset, our methods outperforms or is comparative to state of art for all classes. Here we test our method on AEHF bin picking dataset. The dataset is more challenging since the scene is more cluttered with severe occlusion and multi-object in it. And results shows that our method outperforms state of art with a large margin, which also proves that our method is robust. We also build a graph system to further test our method. The system integrates 8 parts per minute. The system integrates the buzzer and Kinect interfaces and can grasp 8 parts per minute. So here I will introduce some deep learning based methods. These methods often rely on detection or segmentation methods to generate region of interest here, and then the features in the region are set into post estimation head and use classification or regression method to predict the post parameters. And for example, SSD use the SSD detector for detection and estimate the pose by classify the view ID and the in-plane rotation ID. And post-CNN use 3 heads here to predict segmentation and location and orientations. However, the above methods have several limitations. And first, the accuracy of the pose is limited by the performance of detection of segmentation methods. And then secondly, the pose is derived from 2D data and suffers from loss of geometric information. And finally, they need heavily annotated and hard to generalize. So our key idea is that we combine the powerful feature extraction ability of deep learning-based methods and use more robust accuracy and more accurate traditional voting strategy. So here is our work, and the main contribution is that we propose a simple but effective and supervised feature encoder for point cloud-based local 3D feature extraction. And this is pipeline. First, takes 3D position, RGB, and normal as input, and do one-dimensional convolution and export to get a global feature, and the local and global feature are stacked and sent into the next layer. In addition, the proposed feature can perfectly preserve the geometric information using an encoder-decoder architecture here, and the reconstruction quality is on the right. So here is the main pipeline. We still apply the robust indirect voting based strategy. It is the same as the VSLPS. So here are results on LCHF dataset, and our method leads on all classes. Here are some qualitative results, and we can see that the votes are clearly clustered in the object centers. We then test on lemon dataset, and it's more cluttered and with heavy occlusion. Here the results on the model of different scales are shown. We can see that our method is suitable for all scales. And our method outperforms both traditional and deep learning-based methods, such as SSD60. So in conclusion, we propose a traditional geometric feature, VSLPS, which introduces the line of sight to eliminate ambiguity of LRF, thus achieves more efficient and accurate performance. In addition, we propose an unsupervised geometric feature encoder that it can be directly applied on point cloud and avoid the loss of geometric information. And currently, most post-animation methods focus on the instance level and estimate a rigid transformation. And category level and non-rigid post-animation are challenging. And in the future, we will also focus on these problems. So that's the end of my talk, and hopefully it's interesting and helpful for you. Attention.
Okay, thank you. Questions? Okay, I have one question. Because you mentioned in the traditional method called LRF, when you estimate the orientation of the object, you said that you use the icon vector, right, to estimate the orientation. But you said for the if this data set, the shape is locally symmetric, that means it will have ambiguity, right?
Yeah.
But you know what? This ambiguity not relies on the shape, we say symmetric, but also on the distribution of the sample, the data set. For example, if a square or a round or circular or something, if you sample different sample, if they have different density, then you will have this different icon vector. How can you explain this?
Basically, I think we focus on the local features, and so I think I can extract different local features of different models. So I think this problem is still exists, since if the object you want to detect or estimate the pose of a sphere, then all the local features are symmetric, so then you can't estimate each pose or something like that.
Yeah, okay. Yeah, thank you. Any more questions?
Thank you.
Okay, thank you. Okay, now we move to next speaker. Okay, now it's Qian Jiaming from Nanjing University of Science and Technology. Okay, now let's welcome.
Okay, thank you for the introduction. And hello, everyone. My name is Jiaming Qian. I'm from the Nanjing University of Science and Technology. Today, my topic is high-resolution real-time 360-degree three-dimensional surface defect inspection with fringe projection profilometry. With the advance of industry manufacturing. I'm very sorry. With the advance of Industry 4.0, the traditional manufacturing industry accelerates towards intelligence. In the field of intelligent manufacturing, how to ensure high-quality standards through rapid and accurate inspection technologies is one of the biggest challenges. Nowadays, The 3D optical quality control has become one of the most important inspection technologies because of its more reliable accuracy and higher efficiency than traditional manual inspection methods. The 3D optical defect inspection method is usually to first obtain all the 3D shapes of the object and stretch them into a complete one, and then register the measured data and the standard model, and finally calculate the deviation between them. In the whole process, how to realize the fast 3D registration, including the registration between the measured data from different views and the registration between the measured data and the standard model, is the most difficult. To achieve this, some additional equipment such as robotic arms and special clamps are needed for position control. However, these devices are very expensive and will make the whole system more complex. In addition, the means of first obtaining all the 3D shapes of the object and then performing the post-processing inspection is still time-consuming. A more ideal way is to realize real-time 3D inspection without any additional equipment for position control. So in this work, we propose a high-resolution real-time 3-dimensional surface defect inspection method without using any additional equipment for position control. Whether for real-time point cloud registration and real-time inspection, the real-time 3D information acquisition is the first step. In this work, we use the fringe projection profilometry to reconstruct the 3D information of the object. In FPP, some fringe patterns are projected onto the object and then captured by the camera. With the corresponding decoding algorithm, we can reconstruct the 3D information of the object. The two main phase analysis technologies of FPP are the phase shifting method and the Fourier transform method. Since accuracy is very important for inspection, we choose the phase shifting method. Meanwhile, considering the efficiency, we finally use the 3-step PS method. With 3 fringe patterns, we can easily get the webbed face. To unweb the webbed face, the common method is the temporal face unwrapping method. However, with this method, we must project a lot of fringe patterns with different frequencies, which reduce the 3D imaging efficiency. In this work, we use the stereo face unwrapping method, which can remove the face ambiguity without protecting any additional fringe patterns. The principle of SPU can be seen in this figure. For point 0.01 in camera 1, it may have n possible fringe orders, with which n possible 3D candidates can be reconstructed by camera 1 and the projector, where n is the number of the used fringes. These 3D candidates can be projected onto camera 2 to get possible 2D candidates. Among these 2D candidates, there must be a correct matching point, which has the most similar unwebbed face value with 0.1. Then the face consist check is performed to find the matching point, and the ambiguity of 0.1 can also be removed. With SPU, we can realize real-time 3D information acquisition without protecting any additional fringe patterns. To perform inspection, there must be a standard reference, which is usually an exciting CAD model or a complete scanned 3D model of a standard object. In this work, we focus on the latter to create the standard library. To this end, our previous work of high-resolution real-time three-dimensional model reconstruction method is utilized. Firstly, we use the shift algorithm to find the 2D mapping points of two adjacent 2D images. With the found 2D matching points and their corresponding 3D points, we can closely register the point clouds of two adjacent time. Then ICP is used for fine registration. However, ICP is time-consuming and is not suitable for real-time scenes. To improve the registration efficiency, we propose a two-thread mechanism to realize fine and coarse registrations at the same time. We use the sum of two norms of the transformation matrices during each coarse registration to quantify the motion value of the object. The ICP-based fine registration will not be performed in another thread until the cumulative motion reaches a certain thread. The whole process of our real-time 3D model reconstruction method can be shown in this figure. We first use the shift to find 2D mapping points. With their corresponding 3D points, we can realize coarse registration. Then we quantify the motion value of the object. If the cumulative motion value reaches a certain threshold, the fine registration is performed in this thread. Meanwhile, the coarse registration continues to be carried out. With this method, we can quickly reconstruct the complete 3D model of a standard object. We assume that there are total H effective registration elements. Then we rotate the scanned standard model to the original pose of each 2D image. And we storm these 2D images and these rotated standard models as the standard library. Then we can perform the inspection. Here shows the 2D image IC and the 3D data XYZC of the measured object at current pose. We first use the ORB algorithm to find the 2D image in the standard library, which has the most 2D mapping points with IC. Then we again use the shift algorithm to find the more accurate 2D mapping points. With the found mapping points and their corresponding 3D points, we can realize the coarse registration between the measured data XYZC and the standard model. Then the ICP is used for fine registration. Now we will discuss the difference calibration between the measured data and the standard model. For point O in XYZC, its matching point is P. Different compared with P1 to P4, P has the closest distance with O. Based on such factor, we use the smallest 3D distance between O and all the 3D points of the standard model to quantify the 3D defects of O. With such minimal 3D distance searching method for all the points of XYZC, we can obtain its 3D surface defects. In order to further improve the inspection efficiency, we propose another two-thread mechanism to perform registration and detection at the same time. The whole process of our inspection method can be shown in this figure. We first use the ORB algorithm to find the 2D image in the standard library with most 2D mapping points with IC. Then the more accurate 2D mapping points can be determined by shift. With their corresponding 3D points, we can realize the coarse registration between the measured data and the standard model. Then ICP is used for fine registration. Finally, the minimum 3D distance searching method is performed to obtain the 3D surface defects of the measured object. Meanwhile, the scanning and registration between the newly scanned 3D data from another view and the standard model continues to be carried out in the registration thread. To prove our method, we construct a SPU-based 3D imaging system, which includes 4 cameras and 1 projector. Its speed is about 45 Hz, and its accuracy is about 45 microns. Its whole registration accuracy is about 100 microns. We first use our system to measure a David model. And as can be seen in this video, we just rotate the David model by our hands arbitrarily, and our system can well align the measured data from different views. Here, the middle shows the single scanning result, and the left shows the registration result. After obtaining the 3D model of David, we can use it to create the standard library. And we can see that the data from different views are well aligned. Then we passed some paper in David's notes to simulate defects. And we rotate the defective David in front of the system, and our software can quickly detect the 3D defects of the defective David. The time for single registration and inspection is about 2 seconds and 1 second. Here shows the final inspection results of our method, from which we can see that the regions with defects are well detected. We also use our method to inspect a workpiece. Figures A to C are the standard workpiece. Figures D to F are the measured workpiece. Figures G to I are the inspection results of a professional 3D point cloud processing tool MeshLab. And figures G to L are the inspection results of our method, which is very close to those of MeshLab. These experiments can prove that our method can provide fast and high accuracy 3D surface defect inspection. This is our vision for the future. We think that our method has the potential to provide full inspection of the workpieces, the inspection results of which can be fed back to the production line to adjust the production process in time. Thank you very much.
Okay, thank you. We got one question from the audience. They ask that because you say you can realize real-time registration for such object, but you rotate it manually, right? So is any limitation on the rotating speed?
Because the method of our 3D information acquisition is three-step fringe projection method. So if the object is rotated too fast, it will cause some motion rips. So the object can only rotate it slowly.
How slow?
We didn't quantify how slow.
Okay, good. I got one question anyway. Because you said because on the first slide you said you mentioned the intelligent manufacturing. That means you want to inspect the actual some defect. I mean, what kind of actual defect you want to detect? Because later on you establish one reference artifact and compare the actual workpiece with the reference one. That means, such three-dimensional projection, it has a very, very low sampling density. That means the lateral resolution is very, very, is poor. That means for the small defect, like cracked, you cannot even detect. You cannot recognize. That means, actually, what kind of defect can you really detect?
Okay. Our method is to detect the surface defects, and since the whole registration accuracy of our system is about 100 microns. So if the defects is larger than 100 microns, our system will, I think it will go to fail.
Okay, good. I hope next time we can know, your detailed validation for the small defect, so that you can prove your lateral and vertical resolution. Okay, good. Thank you.
Thanks.
Okay. Now we move to the next one. Is Mr. Liu Zhenqi from Fudan University talking about deflectometry. Okay, let's welcome.
Okay. Good afternoon, everyone. My name is Zhenqi Liu from Fudan University. I'm honored to give this report, and the title is Analysis and Compensation of Aberration-Induced Errors in Phase Measuring Deflectometry. The outline includes 5 aspects. Currently, aspheric and And the freeform optical surfaces are widely applied in various cutting-edge equipment and high-precision instruments. The form quality of these optical surfaces are crucial to their functionalities. Currently, there are two kinds of measuring methods, including interferometry and profilometry. However, they are not suitable to measure the freeform optical surfaces, and those methods are sensitive to environmental noise. We can use the deflectometry to measure the complex optical surfaces. In the deflectometric system, a point at the LCD screen brightens the corresponding pixel at the camera via the reflection from one measured point M. The fundamental principle is to obtain local slope of surface under test that can be calculated through the incident ray I and the reflected ray R. And the advantages of deflectometry includes non-contact operation, full-field measurement, fast acquisition, and high precision. In the deflectometric process, the camera firstly captures the distorted fringe patterns reflected by the measured surface under test. Then, the wrapped phase can be retrieved by using the full-step phase shifting method. By using the multi-frequency method, the unwrapped phase can be obtained to calculate the pixel packets between the camera and the screen. Then, the gradient map can be calculated by using the angle bisectors between the incident rays and the reflected rays. Finally, the 3D surface can be reconstructed from the gradients. Henceforth, the phase accuracy affects the corresponding precision between the camera and the screen, which impacts the measurement accuracy. Unfortunately, deflectometry suffers from the problem of position angle uncertainty. If the camera is focused on the screen, the detected point will be a large spot, thereby decreasing the position accuracy. And in the second situation, the camera can be focused on the surface under test. The position accuracy can be guaranteed, but the screen must be defocused to decrease the angle uncertainty. Therefore, they have a Heisenberg uncertainty described in this function. A common deflectometry configuration focuses on the surface under test to get the high accuracy position. Therefore, the screen must be defocused to blur the captured image. Then there is a blurring issue to reduce the phase accuracy. The imaging model can be described as this function. H is the blurring kernel, also named as the point spread function. G phi is the ideal image. The captured image is the convolution result between the blurring kernel and the ideal image. If the PSF is unsymmetric because of the comma, the blurring kernel can be make the faces demodulation from the distorted fringe bias. The local forms and the local curvatures of the freeform are different. Therefore, the blurring kernel caused by the defocusing and the optical aberration varies with different surface regions, like this picture. So a common PSF cannot describe the whole aberration. A space variant PSFs are significant to provide the more accurate blurring kernels. Here, we introduce a 4D light file to describe the light transmitting relationship between a screen pixel XY and a camera pixel UV. The PSF associated with a screen pixel can be extracted from the light field L, and the 4D light field can be built by using the Fourier compressive sensing method. The first step is to reconstruct the light field matrix. A series of fringe patterns are displayed on the screen with different frequencies, and the blurred images are captured by the camera, which are convoluted between the light field and the displayed pattern. The complex transform spectrum can be calculated by using the four-step phase shifting strategy. Light field of one camera pixel can be obtained by using the inverse Fourier transform. By traversing all the camera pixels, the full light field matrix can be obtained. To reduce the computing cost, the screen is divided into some patches. In each patch, the above procedure of light field calculation can be processed. In each patch, a central single pixel can be regarded as the point source to estimate the PSF. The second step is to estimate the space variant PSF. In the light field, point source coordinates as the screen can be extracted. The light transmitting matrix corresponding to these point sources as the screen can be extracted to construct the space variant PSFs. The captured image is the convolution between the PSFH and the ideal mapping of the displayed fringes. If we view from the frequency domain, the ideal image can be calculated by using the division operation. However, the blurring kernel H is a low-pass filter, so that in the high frequency spectrum, the result can be affected by the noise. Generally, the Wiener deconvolution method is applied to improve the numerical stability by using a damping parameter lambda. However, the damping parameter lambda is an experimental value, which can be affected by the manual intervention. In order to solve this problem, a least square merit function is constructed to adjust the damping parameter lambda. So we can compensate adaptively the phase by using the optimization strategy. A germanium infrared aspheric lens with a 10 mm aperture is measured to verify the proposed method. This function is the nominal model of the freeform. To reduce the computing cost, the screen image is divided into 35 by 35 patches, and each patch of 15 by 15 pixels is encoded by using fringe patterns with 9 different frequencies. From the space variant PSFs, they show significant difference, and the PSFs located in the outer region are obviously elongated. The reason is that the curvature at different regions of the surface under test varies remarkably. Then comma and astigmatism occur in the off-axis measuring in system. Henceforth, The aberration is more serious in the outer region, as shown in the phase deviation map between the compensated phase and the original phase. The corrected phase at the outer region differs remarkably with that without correction, while the phase at the central part performed similarly. Is consistent with the distribution of PSF. The surface form is reconstructed from the slopes calculated by using the phases with correction and without correction, respectively. For the purpose of quantitative comparison, the surface is measured by a profilometer loop scan as a reference. The measurement results are fitted using the first 36 terms of the Zernike polynomials. The piston and the tilt corresponding to standard Zernike terms from 1 to 3 are removed because they are relevant to the pose of the workpiece rather than the form. The proposed method obtains a better result that is closer to the result by the loop scan compared to that without correction, especially in the third column. The RMS of the total departures in the terms from Z4 to Z15 are 85.78 nanometers after phase correction and 362.50 nanometers before correction, respectively. The main contribution by using the proposed method is reflected in the terms from the low frequency to the medium frequency terms from Z4 to Z15. In summary, this paper proposes a stable estimation method of space variant PSFs. Adaptive phase correction for complex aberrations is proposed. The position angle uncertainty problem is overcome. Thanks.
Okay, thank you. Any questions regarding his talk?
Okay.
Okay, because you said you want to measure some freeform surface, that means the curvature and the resulting focal length will be different at different regions. So that you need to divide the whole screen to different patches. I mean, how can you balance the number of patches and the size of each patch and with the actual shape complexity of the surface under test?
The size of patch is set according to the size of calculated PSF. So we must so the image is divided into some patches according to the size of the estimated PSF size. Okay.
I mean, how? What's the relationship?
Because we because we must calculate the whole image. However, the PSF is space variant, so we must process the image by patch by patch, and the size is set by the size of the calculated PSF. So we patch the we set the size is 3 times of the PSF size, and after calculation, we remove the outer region. The central part is remained to restored and repeatedly processing this process. We can calculate the whole image. Okay.
Okay, thank you. Yeah, good. Okay, now we'll close this session. I will pass the time to Dr. Hu. And now it's time for the coffee break. Please come back at 10 minutes later, okay? We'll have the last 3 talks, okay? Thank you so much.
Okay, our session will begin in 1 minute. And there are last three speakers in this session. So are you ready? 张宇哲.
Yes,
You can
Dr.
share your
Wu.
screen now. Okay. Zhang Yuzhe is a PhD candidate at Huadong University of Science and Technology. His research direction is online measurements of metal additive manufacturing. His presentation title today is Online 3D Measurements of Selective Laser Melting Additive Manufacturing Process. Okay, let's welcome him.
Oh, thank you, Dr. Hu. Ladies and gentlemen, good afternoon. I'm Zhang Yuzhe from Huazhong University of Science and Technology. It's a very great pleasure indeed for me to be able to attend this meeting. The topic of my report is online 3D measurement of powder-bed fusion additive manufacturing process. This is the main content of my report. It contains 6 parts. The first is the research background. With the rapid development of high-end manufacturing in recent years, people have higher and higher requirements for the performance of components. In many productions, highly customized components are required. We also need to design more complex structures to meet more special needs. In aerospace, medical, and other fields, even intelligent components have become a new demand. All the above ideas have a common solution, that is additive manufacturing. Metal is the most widely used material in industry. Therefore, research on metal additive manufacturing is very extensive. And many metal AM systems have also been developed. Our work is mainly related to PBF-AM. This process uses laser as the heat source and metal powder as material to form components. The recording blade spreads the metal powder on the build platform layer by layer, and the laser beam selectively melts the powder. This process continues to circulate, eventually form the components. The speed of heating and cooling during the PBF process is extremely fast. Moreover, this process often has the phenomenon of local overheating. These are likely to cause a variety of defects. The result is that the components formed by the PBF process are lack of stability. The optical measurement we used is more concerned with the surface quality and the geometric accuracy. Many researchers around the world are trying to study online measurement of PBF process, but they have several common problems. Firstly, most researchers use a single camera for measuring, so it's impossible to reconstruct 3D data. Secondly, there is no clear signatures to identify various defects. The second part is the measuring equipment. The first picture is the PBF machine we built by ourselves. At the top of the machine is the laser and scanner. Besides them is the measurement system. Our measurement system consists of 2 cameras and a projector. The picture on the right is the online measurement experiment we did on the PBF machine. It can be seen from the figure that 2 measurements were taken. This is the flow chart of the PBF online measurement process. After each layer of powder is spread, the software will take a measurement, and analyze the powder by topography. After the laser processing, we will take another measurement and analyze whether there are defects. The third part is the measurement of topography. PMP is a common 3D measurement method. We project a series of sinusoidal images on the surface of the components. We used the four-step phase shifting method. Then the principal phase value is solved as Formula 3. Generally, we need a phase unwrapping algorithm, but with this method, we must capture 12 images to perform accurate calculations. That's too slow to be used for online measurement. So we proposed an enhanced PMP. Instead of phase unwrapping, we directly find the corresponding points from wrapped phase maps. The ePMP contains two parts. The first part is disparity range concentrate. DRC can decrease the number of false candidates. Considering the limited thickness of powder during PBF processing, the search area can be narrowed down to the short line of 1 to 2 millimeters length, which is the red line in the picture. This increases the stability and the speed of corresponding point search. However, there are still several existing mismatched points. To solve this problem, we perform another part of the ePMP, image correlation concentrate. The correct corresponding points should have the max correlation value. In this work, we use a commonly standard called normalized cross correlation, which is given by Formula 4. Therefore, the accurate corresponding points can be obtained through the proposed ePMP method. In order to test the accuracy of this method, we designed this experiment. The object to be measured is two standard ball gauges. We measured them 41 times and reconstruct the 3D data. Then we calculate the distance between the centers. It can be seen from the result that the deviation of the center distance is less than 0.03 millimeters. The average deviation is about 0.0183 millimeters. That meets the actual production demand. The following pictures respectively show the flatness data of normal and flawed condition of powder spreading. The 3D height map of defects has different STD. The STD of a normal condition is only 0.0668 millimeters. However, the STD of the defects caused by lacking powder is 0.2334 millimeters, which is 4 times the normal situation. We can detect various key 3D geometric features of the powder bed, such as the position, size, and depth of the defects. The figures below show the surface data of fusion areas. 28 watt is the best process parameter. We can clearly see the sinking depth of the component surface. We can also find that as the laser power increases, the sinking depth increases too. Therefore, we can obtain rich information such as the sinking depth, the flatness, and the boundary of the fusion area. Based on above techniques, only 3 images are required to achieve the 3D measurement, and the speed can be remarkably improved. We can monitor the geometric signatures, including flatness, holes, and some other defects of the powder bed. At the same time, warping, surface runoff, and more defects of fusion area can be also detected by this method. More importantly, we can quantitatively measure these geometric features. Next is the measurement of 3D counter. Counter detection is a basic task in image processing, and it has been dealt with from many different ways. The level set is one of these traditional methods. The main process of this method is to force an initial counter omega to be close to the image eye. Its precision can reach some pixel. However, we usually need to iterate hundreds of or even thousands of times to get an accurate result. That would cost a lot of time. Most of the time wasted is spent on a large number of iterations. At the same time, some false counters out of the fusion area can be also detected. Therefore, we generate an original mask M0 from the slice model. Then the mask M0 is processed to create the image masks for the two cameras, and the 3D counter data can be calculated. This method significantly increases the speed and accuracy of the counter detection process. As shown in figure A to C, the counter detection results are given. By the aid of the slice model, the number of iterations has been reduced to 20, which is nearly 10 times faster than the traditional method. This will contribute to improving the accuracy and speed of level set method. However, it's not fast enough. So we propose a face-guided fast counter detection method. We noticed that during the processing of the same layer, only the image of the fusion area changed. Therefore, we can use the different phase information to determine the position of the forming area. Subtract the absolute phase value in the two images. Through a threshold processing, we can get the target image. After getting the target image, we can find that there is still a lot of noise. In order to avoid blurring the edges, we use a low-rank sparse decomposition method to remove noise. First, decompose the target image into a denoise matrix L and a noise matrix S. Then use the classic PCA method to solve L and S, and introduce a compromise factor to transform this issue into a single objective optimization problem. Finally, the Sobel operator is used to calculate the gradient of the image. Then use the skeleton extraction algorithm to determine the true counter of the fusion area. Then a reconstruction method is conducted to obtain the 3D counter data in this layer. Based on the collected data above, the counter accuracy can be calculated as shown in figure F, and it's an important geometric signature for the PBF process. By staking all the counter data, a digital 3D volume for the counters is created. This offers an opportunity to inspect the outside counters of the solid part in real time. Such geometric signatures may contribute to adjusting the process parameters for the PBF process. We introduce the DICE index to judge the accuracy of our counter detection. From the results, we can see that the level set method has a better accuracy, while the face-guided method is much faster. So we can conclude that the face-guided method can be used for online measurement, and the other one can be used for offline. Part 5 is the experiment result. To test the resolution of the measurement system in the deep direction, we designed this component of ladder structure. This component consists of 14 steps, and the height of each step is 0.03 millimeters. The precision of confocal laser scanning microscope is only 8 nanometers. We can regard these measurement results as the true values. We measured the average height of each step, then compare the result of our method with the one of CLSM. The max deviation is only 1.9%. That means the accuracy of our method can meet the needs of actual production. This is the software we use for online measurement. It can preview the images captured by the two cameras. If you press the button of topography analysis or content analysis, it will pop up the corresponding window. The last part is summary and outlook. The EPMP we proposed improves the speed and accuracy of matching points in the 3D reconstruction process. The level set method assisted by the slice model and face-guided fast counter detection improve the speed of counter detection. At the same time, we also have other ideas. If the layer thickness is very small, how to ensure the accuracy and speed of 3D reconstruction and counter detection? We will also try to find the relationship between measurement results and process parameters to achieve feedback control. If you have any questions, you can send an email to this address. Okay, that's all. Thanks for your attention.
Okay, nice talk. Here I have one question from an audience, online audience. It's from a Bilibili. His question is about after each 3D measurement, is there a feedback control of the measurement, and how can the feedback control be achieved?
So thanks for this question. That's exactly the key issue we need to study. Actually, the work we are currently completing only includes online measurement and analysis. As I said in the outlook, we are trying to find the relationship between measurement results and the process parameters. For example, through the experiments, we can obtain the surface roughness of parts processed by different laser power. Then we can explore their relationship by deep learning methods. Therefore, we can realize the feedback control.
Okay, and I have a very short question. So which part do you think is the most difficult in your method, and how did you overcome it?
Let's find this page. I think the most difficult part is this EPMP, the first part of this EPMP, because we have to find some concentrate to short our measuring time. So we have many experiments, and at last we find this the thickness of the second. Let me find. So we find this thickness concentrate. We spend a lot of time to find this. So I think that's the difficult one.
Okay. Okay, thanks again.
Thank you, Dr. Hu.
So let's welcome next speaker, Liu Yue. She is a PhD student of precision metrology at the University of Huddersfield Center for Precision Technologies. She got her master's and bachelor's in Hebei University of Technology. She focused on measurement instrument research, additive manufacturing techniques, range projection propylometry, and phase measuring deflectometry. And her presentation title is In-Still Inspection in E-beam AM Machine Based on Fringe Projection Propylometry. Okay, let's welcome her.
Okay, let's share my screen. Okay, and I will present today a topic about in situ quality inspection in electron beam additive manufacturing based on fringe projection propylometry. And my name is Liu Yue. I come from University of Huddersfield in UK. I will divide into these 5 parts and briefly introduction, a methodology about the principle of this technique and our system calibration, implementation, and future developments. So as we know, additive manufacturing is a layer-wise creation of objects with complex geometrics, which include internal features. And of our developed system, our challenge is to build an effective in situ, layer-by-layer calibrated measurement method to obtain planar and out-of-plane printed parts and powder delivery. It is allowing to look at quality during the AM build process, and our particular in a new electron beam machine. This project, which is developed under the Innovate UK funding and is between the University of Huddersfield and the UK newly company called Wayland Additive, and they develop a new electron beam additive manufacturing machine, cooperate with several new concepts. So the measurement task for this project is to build a new system to inspect the new powder delivery, pre-melting, and inspect each layer after build post-melting to detect in and out of plane distortion, hopefully to detect parts defects and to know the quality. So both of these two process, we need to finish test last 5 seconds. And the resolution is around 50 micrometers, and the field of view is around 200 by 200 millimeters. So the measurement we settled down was the sinusoidal fringe projection techniques. These techniques can provide high accuracy and high point mapping through extraction the angular phase of a projected pattern from every pixel in an image. And it also has many advantages like non-contact operation, full field acquisition, high accuracy, and regular faster data processing and low cost. And it is also can be used in any other applications like reverse engineering, facial recognition, and industrial inspection. So what was the logic? After the powder delivery, we will do the first time inspection for the powder bed. And if the powder delivery is successful, we continue the melt process and to do the second time inspection for the finished parts. In this both process, when we find any problem, we can do the second time powder delivery or to hold the build. So next is methodology. The principle of this technique is triangulation and mirroring fringe distortion. We establish the relationship between the CCD camera and the projector, and by equation 1, and we can using Taylor expansion to a simple one. Then after the system calibration, we can get the height information from the face. So system calibration we also use two calibration boards, chessboard and circle ring board. About the system calibration, we need to finish camera calibration, depth calibration, and transverse calibration. For the camera calibration, it's just use a chessboard to put it in the depth of field to pose in different angles and positions to obtain camera internal parameters and to do the camera lens distortion correction. And next is depth calibration. We use a circle ring board, put it on a transfer stage, moving to several known positions. And the main task for this, we need to calculate the coefficients of this equation. And the left parts, we can get the height information from a radial interferometer and to help us to measure the moving distance. And the right side, we at every moving positions, we project sinusoidal fringe patterns, and we can get unwrap the face. Then we can get the coefficients. And we also the ceramic. The material of this calibration board is ceramic, and the accuracy is around 15 millimeter. And we set the middle position as a reference surface, and then we can finish the calibration. And the next is transverse calibration. It is also to calculate the coefficients of these two equations. We can get x and y value from this circle ring board in the world coordinate system, and the right side z value come from the interferometer, and then we can calculate the coefficients. That is a flow chart to show here about the transverse calibration. And during this calibration, the black circle ring will impact the face and will bring phase error. So I use a fitting algorithm to solve this problem. After fitting, I use a get a smooth and flat unwrap the face to replace original one. That is the compare result before correction and after correction. And we can see this problem have been solved well. And that is the evaluation of this system. I use two methods to evaluate this system. First, I measure the moving distance by the interferometer and compared with I measured result. And absolute error is around 6.9 micrometers, and the standard deviation is around 16 micrometers. And also I measured standard ceramic step gauges, and this one is used for evaluate the Z direction and resolution. And we also can see the resolution is around 20 micrometers. That is the real electron beam machine, because the melting source is electron beam, so the inside chamber is vacuum. So we put our system on the top of the machine via these two ports to view the powder bed and finish the parts to finish the test. And we also develop interface software, and this one is an example to show here. We can see some defects here, and that is a control software we use to do the measurement. We project the sinusoidal pattern onto the surface. We can see the fringes here. And that is the finished parts on the left image. And for the right side is the data collected from our metrology system. And this from this dependent measurement from a roller arm. And this is a video we do the measurement during the manufacturing, and it takes every 15 layers, and we can see some small expansion here, and we can design, we continue the build or stop it. And that is another example for excessive powder delivery because the rake damage. And we can clearly see the results here. And next is after the electron beam melting, the surface will become shiny if we use the same parameters to take the images for the powder bed and finish the parts, and then we'll have the overexposure problem. We will lose some data here, so we need to solve this problem. For now, we try to do multi-explorer to merge them together to solve this problem. And from these results, we can see the short explore time and a longer explore time, and merge them together, we can get a good result. So the next step, we need to solve the reflective problem, because the reflective properties of the metal surface change when the new beam process parameters or scanning strategy vary. And we next step, we want to add machine learning to solve this problem. A brief conclusion and future work. An in situ monitoring technique has been developed to inspect the powder bed and parts using a fringe projection technique, and a calibration procedure developed and try to use different explore time to obtain shiny surfaces. And in the future, we want to add machine learning to solve explorer problem, and integration of machine learning with sophisticated process feedback. I would like to thank you EPSRC funding for Future Metrology Hub and Innovate UK for funding the RAM-up project, and also thank to the Chris Smith from Wayland Additive. Yeah, thank you for your attention. That's all. Thanks.
Okay, thanks for your nice talk. I have a question. What is the phase shifting number that is used in your phase calculation, and how do you select these numbers in the temporal phase unwrapping?
Sorry, could you repeat, please?
Okay, the phase shifting is phase shifting in use in your method?
Yeah. Yes.
So what is the phase shifting number, and how do you select or determine the number?
Okay. For now, we use a 4-step phase shifting, and actually, it's better to use more steps phase shifting to solve nonlinear problem. Actually, we have also correct the nonlinear effects. So for now, 4 steps phase shifting is okay for our measurement.
Okay, so have you tried to use your 3D measurement system in the inspection of other kinds of materials?
Yeah, sure. It is also can be used in other material if the surface is roughness. And in the next step, we need to solve some reflective surface, like this, because when we use different power source to melting the powder bed, and the surface will become the reflective rate will will change. So next step, we need to solve this problem.
Okay, thanks again.
Yeah, thank you.
So next is our last speaker. Okay. And it's Zhu Zexuan. He is currently a PhD student at the University of Auckland. He joined the Laboratory for Industry 4.0 Smart Manufacturing System Research Group in 2018. His research interests include augmented reality in manufacturing, cyber-physical machine tools, and digital twin technology. His topic today is augmented reality assisted machine process for smart manufacturing. Okay, let's welcome him.
Okay, can you guys see my screen?
Yes,
it's all good. Okay, thanks for the chair. Thanks for the instruction. So good afternoon, everyone. Welcome to my session and join my presentation today. My name is Zexuan Zhu, and I'm currently a PhD student at the University of Auckland. My research focus is the application of augmented reality in smart manufacturing. And the topic I'm going to talk about today is augmented reality assisted machining process for smart manufacturing. So in this work, AR technology in manufacturing provides various possibilities for advanced human-machine interactions, which allows machine tools to achieve real-time machining process monitoring, machining simulation, process optimization, and workpiece 3D modeling update. Right. So here's the outline for my today's talk. I will firstly introduce the background of this research, and followed by the proposed system architecture, and also a case study to demonstrate the proposed system. And then a conclusion will be given at the end. So if you are not familiar with the Industrial 4.0, here's the diagram. This is the evolution history of industry since 18th century. At that time, people tried to use steam power to drive different machines to accomplish the jobs in a more efficient way. Even the key technology has changed through the history. The ultimate goal for each revolution in industry aims to provide better manufacturing environment towards the world. Especially in fourth industrial revolution, it comes with more requirements for the industry, such as shorter development periods, individualization on demands, flexibility of production lines, and the decentralization and the resource efficiency. And for smart manufacturing, it is a broad category of manufacturing that employs computer integrated manufacturing, high levels of adaptabilities, and the rapid design changes, digital information technology, and also more flexible technical workforce training. So being accompanied with the revolution in industry and the high level requirements in manufacturing, the evolution of machine tools is also significant. In today's industry, the machine operator required to control and monitor different machine tools at the same time. With machine tool 4.0, total vertical and horizontal integrations become possible. Machine tools will no longer exist as a piece of isolated manufacturing equipment. They can be service and also solution providers. As the fourth generation of machine tool, it has to be smart and intelligent, and it needs to be vertically and horizontally connected in the system. It will be widely accessible through any platform and devices. And finally, it must be more adaptive and autonomous. With the development of machine tools, the following issues are coming up. So first, not all machine tools can achieve the requirements of machine tool 4.0. And the information and the data that we collected from these machines are exponentially growing. In order to present all this information in the data, actual displays are required to present all this information. about the fact that attention will be distributed to additional displays with inconsistent user interface. Furthermore, the modern industrial production in the world market requires a further increase in variety of complex products in every short delivery of time. Therefore, the efficiency for the operation process and problem solving is also critical. So what do we need? With extensive real-time data and computations deeply integrated with machining process, machine tool provides various possibilities for advanced human-machine interactions. But the current human-machine interfaces cannot provide enough and intuitive information to the operators. Therefore, we are aiming to develop and advance the human and the machine interfaces to provide users with the following features: a comprehensive and intuitive perception of the machining process, ubiquitous access to real-time information and applications, instant and distributed decision-making support. So in this case, AR technology turns out to be a key technology to overlay virtual information on the real workspace in an intuitive way through different interfaces. So augmented reality technology is a novel human-computer interaction technology that overlays computer-generated virtual information in the real world. And right now, AR has been widely used in our life, such as games, navigation tools, and architecture designs, and so on. AR can be defined as a system that fulfills three basic features. First, a combination of real and virtual worlds. Second, the real-time physical and virtual interactions, and also accurate 3D registration of virtual and real objects. And also, AR technology has been identified as one of the key technologies in the fourth industrial revolution. That is because with the rapid development of computer and manufacturing technology to allow users and operators to visualize and interact with the manufacturing information associated with the manufacturing processes becomes a trend. AR has been applied in many of the manufacturing fields right now, such as product design, product assembly, digital training, product services, and fabrication monitoring. For example, during the product assembly and training process, with the assistance of AR, workers could significantly reduce the number of errors and the operating. In the product services, it allows the remote and the cloud-based services with a prompt expert guidance. And moreover, in the area of machining process monitoring, it has been applied to display the information of different facilities on the shop floor. However, most of the studies only apply the AR to statically present the information on the monitor, but the interactions and the communications between human and machine tools have been ignored. Therefore, based on our research goals, we are going to develop and advance the human and machine interfaces to provide users with intuitive and consistent real-time machining information through the entire machining process. Here's the proposed framework. There are three main components in this diagram. The physical part, which includes different steps of machining process. The virtual part, which is the real-time reflection and updates from the physical environment. And the AR-enabled human and machine interface to connect both of them. At each stage of the machining process, the virtual representation of the physical objects will provide different supports and features to both operators and the physical machine tool. By establishing and presenting updated workpiece digital 3D models through the machining process to integrate various manufacturing information and data, and significantly reduce the machining time, reduce the unexpected collision and the cost, and also facilitate the operator's decision-making. Before I talk about the physical setup of our system, I would like to briefly introduce the system architecture here. So for our design, we call it AR-enabled intelligent machine window, or Ibindo in short. As you can see here, the physical machine tool combined with external sensors and data acquisition devices, which can achieve multi-functions through our intelligent machine window. And they communicate and interact with the users. Furthermore, users' feedback and commands will also be received, processed, and sent back to the physical machine tool to achieve the closed-loop control. So now in this part, I'm going to explain the physical setup of our intelligent machine window, and also some key features. So as you can see, the setup, the machine tool we are using is the AMCO Concept 1053 axis milling machine, connected with a touch screen monitor here. And inside of the machine, we have capture camera to capture the real-time interior of the machine tool for further processing. And also the calibration board here is used to map the 2D image coordinate with the machine's 3D working coordinate. The calibration results will be used to synchronize both physical machine tool and the generated 3D virtual model. And here is the design of our Ibindo user interface. As you can see, it has integrated CNC control interface with extra multi-function blocks to achieve the advanced machine control and monitoring. It has different control modes, such as decode parser, draw mode, MDI mode, or manual data input mode. And the most importantly is the AR-enabled functionalities. So in AR mode, we can visualize the CAD model, simulate and monitor the entire machining process, and also toggle safety machining volume in real time. The development interface integrated various functions, including real-time CNC control, real-time machining data visualization, AR-enabled process monitoring, and machining simulation, and also in process feed rate optimization. This interface provides an intuitive and comprehensive understanding of the machining processes, while simultaneously allows operators to control the machine tool like using a normal CNC control panel. Here are some features can be achieved by our Ibindo system. The AR-assisted process monitoring can significantly enhance the visibility of the machining process, especially when chips and coolant are blocking users' views in the real machining environment. On the right-hand side, the on-machine simulation results can indicate any possible setup of program fields, and the updated final 3D model can be used for quality checking and further FEA analysis to support the machine operator to make further decisions. And the other key features is the collision detection during the simulation. During the simulation process, when the virtual cutter reaches the dangerous space, a collision alarm will pop up on the user interface, and the emergency stop would be automatically triggered to prevent actual collisions. And any possible collisions will be reported to the operator. This feature can also avoid any unexpected machine downtime and reduce the cost during the real manufacturing environment. And in addition, we had developed our system not only through the attached camera system, but also on other portable devices. The pictures here are captured from our Microsoft HoloLens. As you can see, it also can achieve the real-time machining process and the information monitoring. Even with no physical control panel, the control process through the HoloLens can also be achieved by users' gestures and also voice commands. So here, I prepared a short video to give you a more intuitive presentation of the Ibindo system. All right, that's the video. So in conclusion, the AR-assisted Ibindo was developed as an advanced human and machine interfaces in machining process for machine tools. So it can first provide a comprehensive and intuitive perception of both physical environment and its corresponding digital model. It can also achieve high-fidelity machining simulation in real machining environment with real machining parameters to avoid unexpected collision and machine downtime. It will utilize the updated 3D model for quality checking and also future analysis. It will take advantage of this data and information to perform efficient decision makings and higher level system control. And finally, it can control, monitor, and optimize the machining process in real time through different platforms and devices. Yeah, that's all for my presentation today, and thanks for your attention.
Okay. So Xuan has presented a very nice and clear and also interesting talk about how the AR assists the machine process. So is there any limitations for the application of AR, and do you have any idea to break them?
You mean through for our case study, right?
Yeah, your system.
Or for the setup or for the algorithm, or
yeah. Do you have?
Yeah, I think AR, to achieve the AR. So as I mentioned, we have a large amount of data to transfer during real time, and also no, we just collect the data. We also have to process the data. So I mean, the traffic is quite heavy when we do try to synchronize all the informations through the machine and through our portable devices and through our like computer. So, and that's the latency. Maybe if you watch the video, you may realize that the delay is quite obvious. So we are looking forward to reduce the latency and improve the real time simulation performances in the future. Yeah.
Okay, a very clear answer. So I think that's all about our session today.
Thank you.
So thank you. Thanks. Oh, after the ending, don't forget to get in the other session. I mean the other meeting room to attend the closing ceremony. And good luck. Okay, Professor John, do you have anything to declare? Okay, if
no, yes, sorry, I am mute. So
okay.
yeah, I think we thanks for chairing this session, and so I think everyone should go back to the other room, plenary room, or the keynote room, and I think they are close to finish that session as well. So then we will attend. We'll have this ceremony over there. Thank you, everybody.
Okay.